Hello, everybody. Welcome to my AP Calculus video series. It's called Calculus from the Dome. This is Unit 1, Limits and Continuity. So let's go ahead and get started. So before we go into understanding limits, let's go ahead and go through some, I guess, vocabulary of limits, how to like pronounce these notations. So this first one here, it's read, the limit as x approaches c of f of x equals L. Uh, this next one is the limit as x goes to c from the left equals L. Approaches and goes are used synonymously. So you can just, I'd like to say goes more, but I write down approaches to sound smart. The limit as x goes to c from the right uh, equals L. And that's for this last one here. So these are pretty nice. It's important to understand how to say these. I think a big part of math is understanding the vocabulary first and then going into the understanding so that you can accurately ask questions and things like that. Uh, all right. So let's try to understand limits. So let's say somebody gives you this graph. They say this is the graph of f of x equals x cubed. They ask you to find the limit as x approaches 2. It's 2 right here. This is the approaching number. So you're saying, well, what even is a limit? So a limit is basically just the value that you approach, um, the value that your f function approaches as you plug in or go to your x value, which is 2. So in this case, this would just be equal to 2 cubed. Let me write that better. 2 cubed. And that's equal to 8. Now this is nice. Limits are very interesting because you need to know about a left and right limit as well. So let's go ahead and look at a different problem. Let me just erase this. That one was a simple problem. Most of the time with limits, you can really just plug in the number. But a lot of the time as well, they're going to make it so that's not possible. So let's go and look at left and right hand limits. So let's take a look at this function. Uh, let's see. Like this, and let's make it right about here. Open, closed. Okay. So this is a piecewise function. This is f of x is equal to, and let's say this is x, this is 1, this is 1, this is 2. Okay. So for x less than 1, oh shoot. For x less than 1, we just have the function of x. And for x greater than or equal to 1, we have just the constant function 1. So this is known as a piecewise function. I believe we should know about this by now if you're in calculus already. I believe we go through that in pre-calculus or some other class before this. So basically how these work is that they give you a domain restriction, and they give you your function that's actually there. So in this case, we have, for all x values less than 1, we have this function here. And for all x values, let me go to this color. For all x values greater than or equal to 1, we have this function right here. Okay. And this open dot basically tells us that it's not defined there for x equals 1. It's defined on it's defined on the function 1 over here. So this says undefined and defined. So whenever you have an open dot, that means it's undefined there. And undefined just means that there's no function value when you plug it in there. In this case, the function value would be for f of 1, it would be equal to 1. Just got to plug it in and make sure it's in your respective domain. So when somebody asks you, well, what's the limit as x goes to, let's pick the special value 1, because that's where we see a little jump from 2 to 1, of f of x. Right? Well, this is when you tell them, well, I don't know. So the way to do this is that you check the value going from the left and the right. So we have to take the limit First, we take the limit as x goes to 1 from the left of f. So when we go from the left side, this is these values here, running all the way up until you hit here. Well, that looks like it's going to approach 2. So we can say that the limit from the left is 2. All right. Well, let's see what happens when we approach it from, well, the right. So coming from the right side, along these blue arrows, it appears that when we hit x equals 1, we get to the value of, well, I should probably write this in black. Whoopsies. We get to the value of the limit as x goes to 1 from the right of f of x. Well, this should be equal to 1. So we have kind of a discrepancy between these two values. They're not the same. So when we have a left and right limit not being equal to each other, that's when we get this special case of the full limit. We say it does not exist, or D&E for short. I'm going to write it all out just this once. So that's pretty nice. So it suffices to say that, well, if the limit from the right of our function is equal to the limit from the left is equal to the limit from the right of our function, then we can say that the limit exists in total. So that's pretty nice. And that's actually a pretty useful theorem. You're going to be using this a lot. I know the AP College Board likes to ask questions like this, like so much. There's so many on the FRQs, on the MCQs. Just go ahead and get this down, guys. I'm sure you'll understand it. Just keep rewatching or find other resources if this isn't helping you. Okay, so that's pretty cool. This is basically what a limit is. You just look at the value that you approach when you plug in your x value or get really close to it from the left and the right. And then if they're both the same, then your total limit exists. Yeah. If there's anything more, hopefully I think of it. Oh. There is also, go ahead and erase this. Boop, 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 boop. There's also limits at infinity. Ugh. So to take the limit as x goes to plus or minus infinity of our arbitrary function in this case, or random function, we have to look at, well, end behavior. And I think they teach this to you in pre-calculus, but let's go ahead and go over it. So let's say we had a function like f of x is equal to some polynomial x cubed plus x, right? All right, so if you graph this, I believe this has a root at -1. No, wait. Positive. No, wait. Let's solve for it. All right, it has a root at 0 and I think nothing else. Ooh, I don't know what this looks like. That one's ugly. Let's look at x cubed, guys. My bad. So x squared plus squared minus 4. Let's do that one. That one looks good. This is x minus 2 and x plus 2. So we can go ahead and graph this polynomial. We know it's going to be concave up, which means like a u, and it's going to have zeros at 2 and -2. So we have 2 here, -2 here. Let's go ahead and boom, boom, doo-doo-doo. And we should have a y-intercept at -4. That goes there, and that like that. I know, pretty ugly, but whatever, guys. So, let's say somebody asks you, what's the limit as x goes to infinity of fx? Well, you might be thinking, well, I can never get to infinity. That would take forever, literally. But we can look at values that get really big. So, shoot. So as our values get, oh my god, as our values get larger and larger, going up this red line, and up and up and up forever and ever, we can see that our f values, which is just our graph, is just trending upwards. And we say that this goes to infinity as well. Now, if somebody asks you, what's the limit as x goes to negative infinity of f of x? Well, we just go the other way now. That means we just go all the way to the left of our graph. So let's go and use blue for this. Look at our blue arrows trending to the left side of our function, going up and up and up and up and up forever and ever. It appears that it's trending upwards, also going to positive infinity. So that's pretty nice. So this is a pretty simple example. Let's go ahead and look at it. Different polynomials. Or I guess this is an odd degree polynomial. We'll come to a conclusion that these polynomials all follow some sort of pattern. So if we look at f of x equals x cubed, back at this one, we have this graph here, like so and like so. Okay, all right. So if somebody asks you, what is the, forgot to label these, oopsies. Somebody asks you, what's the limit as x goes to infinity of f of x? Well, we can say that this has to also be infinity, because we can see as we trend upwards here, this pink line of arrows, all the way up and up and up and up, forever and ever, we get to infinity eventually, which is funny. And, well, what happens when you go the other way? That would be asking you the question, what's the limit as x goes to negative infinity of f of x? Well, if we follow our blue arrows, actually going this way, they're going downwards, 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 all the way up to the negative infinity of the y values. So we can say that, well, this will approach negative infinity. Interesting. So looking at these two examples, well, actually, we should probably look at more, but that's fine. I'll just give you guys the whole rundown of it. So if you have a polynomial, oh yeah, plus a bunch of other terms and stuff. We really only care about the highest degree term. If this degree, if n is even, then its n behavior is going to be the same on both going to the left and right. So negative infinity and positive infinity. And then if n is odd, we have different signed n behaviors. So in this case, for x cubed, we had a positive infinity when we went to the right and a negative infinity when we went to the left. But for our quadratic here, for x squared minus 4, we went to positive infinity when we went to the right and positive infinity when we went to the left. So these infinities, they are going to change. If we have a negative coefficient for our leading coefficient, then it's going to flip everything and make stuff different. So if this was f of x equals negative x squared minus 4, well, now we have a parabola that goes down like this. I believe so. Actually, it would be translated up. Whoopsies. Let's not make this a plus. What is this? Minus, yeah. I think now it would look like this. Yeah. So that would go down all the way forever, and then this will make these negative. So basically, what I'm saying is, all you need to worry about is your leading degree, or your highest degree term, and your leading coefficient. So if your leading coefficient is negative, it's going to flip everything across the x-axis. Is that correct? Yes. And if it's positive, it'll stay as you normally think it is. And if your degree is even, then both your n behaviors are the same. If it's odd, both your n behaviors are going to be different. So that's basically the takeaway of limits at infinity for polynomials. Hopefully that's helpful at all. If it's not, so well. Anyway, let's go and look at some limit properties. So here's this first line here. It says that the limit as x goes to a of c times f of x is equal to c times the limit as x goes to a of f of x. So basically it's just telling us that, well, we can pull out constants from the limit. So let's go and look at a nice easy example here. Let's go work in blue because blue's nice. So we can look at the limit as x goes to 3 of 10 over x, right? So we can say our function is 1 over x and pull out this 10. And now we just have the limit as x goes to 3 of 1 over x. So, and in order to evaluate this limit, we just have to really just plug it in. And that's because of this thing called continuity, but we'll get into that in a bit. So we have 10 over 3 as our final answer. All right, that's a nice little example there. This first one is pretty straightforward. Hopefully you guys get it. All right, so now we have the next property. So with the limit as x goes to a of f of x plus or minus g of x is equal to the limit as x goes to a of f of x plus or minus the limit as x goes to a of g of x. So it basically just tells us that we can distribute this limit operator. So we have an operator is just like a function, kind of. Okay, so we have a limit as x goes to, let's go to 5. 5 is a nice number. And then let's look at two functions. I'll look at ln of x, and then plus or minus, let's do plus. And let's look at e to the x, very nice. All right, so this is one nested limit. So then now we can just kind of distribute this limit here. So we have the limit as x goes to 5 of ln x plus the limit as x goes to 5 of e to the x. And that's just equal to ln of 5 plus e to the 5. And this is valid. This is the answer. And if this were a minus, you would do the same thing. So you could translate this to a minus as well. So suffice to say we can do plus or minus. All right, let's go and look at this quotient rule. So we have the limit as x goes to a of the quotient of f and g is equal to the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. And we need to have this extra bit of information that g of x, the limit as x goes to a of g of x, cannot be 0. Otherwise, we would be dividing by 0. Yeah, otherwise we'd be dividing by 0. So let's go ahead and make an example here. Let's see. Let's make something that doesn't cancel out. Yeah, let's do x squared plus 5 over x plus 3. Let's take the limit as x goes to. All right, where was I? So basically, let's make a nice little example for this. Oh yeah. So if we go to, let's go to a nice value of 1 here. So we take the limit as x of x squared plus 5 over x plus 3 as x goes to 1. Well, we can just look at the separate limits, as long as they exist, of 1 of x squared plus 5 divided by of x plus 3. All right. So when you plug in a 1 into the top equation, I guess, we get, our top expression, we get x squared plus 5, where x equals 1. So we get 1 plus 5, which is 6. And then when you plug it into the bottom expression, we get 1 plus 3, which is 4. This simplifies 3 over 2, which is our final answer. And if you go ahead and evaluate it before using the rule, we get the same thing. Because x squared plus 5, plug in 1, you get 6 divided by 1 plus 3, which is 4. 6 over 4 is also 3 over 2, which is what we got. Very nice. Then we can look at this nice little product rule. So we have the limit as x goes to a of f of x times g of x equals the limit as x goes to a of f of x times the limit as x goes to a of g of x. This one's pretty nice too. So as long as both these limits exist individually, they also exist together. So let's make an example here. Let's take the limit as x goes to 12 of, let's look at, nice, x over 2 times e to the x. Let's make sure everything's in parentheses so I can display this property. So now we have the limit as x goes to 12 of x over 2 times the limit as x goes to 12 of e to the x. So this should be equal to, well, when you plug in 12 for x over 2, we get 6. And then when you plug in 12 for e to the x, we just get e to the 12. So this is correct. All right, and then this other last one, let's go to the right example. Whoopsies. We have f of x to the n power. That just means f of x multiplied by itself n times is equal, or the limit as x goes to a of that is equal to limit as x goes to a of f of x all to the n power. So basically we can just take the limit on its base and then just exponentiate, which is very nice. So let's look at an example. Let's look at 1 over x to the 27. And let's take the limit as x goes to 1/7. Yeah, it's a nice little number. So using our properties of x, or our nice little exponent property, we can plug in, or we can like separate this. We just have the limit as x goes to 1/7 of 1 over x, all raised to 27. So this is equal to, well, 1 over 7, or 1 over 1 over 7, which is just to the 27, which is just equal to 7. 27. So that's pretty nice. I'm not going to multiply it out because that's a really big number. Okay, so that's basically all the properties here. What else is there? Oh yeah, there's this idea of continuity. Let's go ahead and look at that. Let me erase this because I already went over it. Okay. Continuity. Very nice. This looks very ugly. I'm sorry. I think I spelled that right. Continuity. Continuity. Sorry, guys. Okay. So we can go ahead and explain what this means. So we look at a graph. And we just kind of like take the limit somewhere. We're going to use this idea of limits. Let's take this limit at, this is the graph of f of x equals x. And this is the limit of, let's say this is 3 and this is also 3. All right? So we can say that f of x is continuous at x, let's call it x naught, at some point x naught, if and only if the limit as x goes to x naught of f of x is also equal to f of x naught. So this is what this is telling us, is if the limit exists and it's equal to the function value at this point x naught, then we have continuity at this point. It's pretty simple. I think it's, you get the hang of it. Just keep going over it. Pretty I think intuitive definition. So let's go and look at some examples here. Let's see, let's determine if some of these graphs are continuous or not continuous. Also another way to interpret continuity, at least in AP Calculus, is, well, if you can just draw the graph without lifting your pencil or pen or Samsung tablet, pencil, pen, pro pen. Yeah. Okay. Let's look at this piecewise function here. I'm not going to give it a definition. I'm just going to write down its graph. So we have f and x, f of x and x. Let's go ahead and look at right here, and it's open there, and it's closed here, and we're going like this. Yeah. Okay, there and there. Okay. And let's say this value occurs at 2, x equals 2. And we can say this is 1, this is 1.5 or whatever. All right. So if I asked you, well, is f
continuous at x equals 2? I know a lot of you would say, well, it's not. But why though? Why isn't it continuous at x equals 2? Well, because I can't draw without lifting my pen or pencil off the paper, right? You see this little jump here? That would require you to raise your pencil and therefore not be continuous. But that's not sufficient enough. We need to explain using this idea of limits and function values. So if we take the limit as x goes to 2 of f of x, we can see that this will give us a d/e, and that's because the limit as x goes to 2 from the left, well, that's equal to 1 of f of x, that's equal to 1. And limit as x goes to 2 from the right of f of x, well, that's equal to 1.5. And that's just because when you're going from the right side, we hit the value 1.5. When we're going from the left side, we hit the value 1. All right? So that already tells us that our limit doesn't exist. So if our limit doesn't exist, well, we can't satisfy this definition because, well, our function value will never be d/e. Yeah, function values can never be d/e unless they're undefined. But yeah, so your limit needs to exist. Can't be d/e. So yeah, that's why we say, yeah, so this tells us that f is not continuous at x equals 2. And if you're confused about what this means, this just means it's like a back and forth statement, you know? So because of all this stuff, that tells us that this was true. And because of this was true, that also tells us that all of this stuff is true. Very nice. It's like a back and forth implication. I don't know if you guys know what that means, but to imply something means to make a conclusion from previous logic. Pretty cool. Okay. Where are we? So this is what's known as a jump discontinuity. Very nice. Let's go ahead and look at a different graph here. Different graph. So we have this, this. Let's make a nice linear line, right? Let's make this one at 4, because why not? This will be 4. This will be f of x, and this will be x, and this is equal to x, because why not? All right. So now we ask the same question. Is f continuous? Well, let's make that this nice little value I made at x equals 4. Well, let's go ahead and try to use our definition of continuity. We say that f is continuous at some point if the limit at that point is equal to the function value at that point. So let's go ahead and plug in this function value. We see that f of 4 is equal to 4. Or actually, no, it's not equal to anything. It's not equal to 4. My bad, guys. I made the example and I mess up. That's funny. It doesn't exist. And that's because there's an open circle here. I'll let you guys know what that's called in a bit, but let's go ahead and find this conclusion to this question. So we have f of 4 not existing. Let's try to find the limit of 4. Limit as x goes to 4 of f of x. So when we go through the left side, right here, let me go do this in pink. From the left side, we get the limit to be 4, because that's the value we're approaching. We're not looking at exactly what it is, not looking at what it's defined to be. We're looking at the value that it gets close to, which is 4. And when we go from the right side, we also get 4. Coming down here, and there. So from the left and right, we get 4. So that tells us that our full limit is, well, it has to be 4. Well, d/e is not equal to 4. So this tells us that f is not continuous at x equals 4. All right. And this continuity is just called a whole slash, I guess, removable discontinuity. Right. Yeah. Actually, I need to fix this definition of the function. So it wasn't actually f of x equals x. It was f of x is equal to, it's x for everything, all real numbers, except for 4, my bad. But it was D and E. Otherwise, this is getting ugly, sorry. So yeah, this is known as a removable discontinuity because we can fill it in if we just change our definition a little bit of f of x. Just make it so that f of x equals x, and that'll let us fill it in. But yeah, it's not continuous because of that hole. Hope this helps. Intermediate value theorem. Very nice. So, here's what this tells us. I'm not going to write it out formally because I kind of forgot how to, but it basically just tells you if you have some 2 points on some interval a to b, and this is f of a, this is f of b, this is f of x, this is x, and it's continuous, which means they're connected. They are connected without raising your hand or whatever, raising your pen, pencil, blah blah blah. That tells us that we have some value in here. F of C. Shoot. It tells you that this value has to exist. There must be a point, at least one point, at which your function crosses this, I guess, threshold. And we can see that this will always be true. So that's basically the rundown of the intermediate value theorem. So you have 2 points, you're connecting them without jumping or any holes. There has to be a value between these 2 points on the y-axis where, or I guess on the y values, where you cross. I don't know, I think it's pretty simple. But then again, I've known calculus for a few years now. Yeah, not the best explainer, but trying to get better, guys. Anyway, that's the intermediate value theorem. Pretty simple, pretty easy, I hope. So on and so forth. Blah, 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 blah. Yeah. So I guess we can go over some practice questions. I'll be right back with some of those. Alright guys, I'm back with some problems. Let's go ahead and try to do these. So, for number 1, it says find the limit as x goes to -6 of f of x and the limit as x goes to 1 of f of x. So let's go ahead and do the first one first. The limit as x goes to -6. So let's go and write it out. Limit as x goes to -6 of f of x. So, let's see where -6 falls in our domain. So -6 is definitely bigger, or I guess less than 1, my bad. So we should be using this function here. Let's go ahead and highlight it just for there. And that's because -6 is less than 1. So when we plug in -6 into this guy, we get 7 minus 4 times -6. 7 minus 4 times -6. Negative times a negative, we get a positive. So that's 7 plus 24, which is equal to, quick maths here, guys, 31, I believe. I hope. Yeah, it should be. Okay, that's the first one done. Very nice. Let's go and take the limit as x goes to 1 of f of x. All right, this one's a little bit different because it doesn't exactly fall in one range or the other. Well, it does when you go directly on it, but this is a piecewise function and it's split off at x equals 1. So we got to check both of these limits. So we need to take the limit as x goes to 1 of -1, or from the left, my bad, of f of x. And we need to take the limits. Shoot. Shouldn't put an equal sign yet. We also need to take the limit as x goes to 1 from the right of f of x. So let's look at the left one first. So the left one corresponds with when x is less than 1. Yeah, because that's coming from the left side. So when x is less than 1, we get 7 minus 4 times 1, which is just 7 minus 4, which is 3. Go ahead and write 7 minus 4 just in case anybody got lost. All right. And then when we go from the right side, we get x squared plus 2. So that's 1 squared plus 2, which is 1 plus 2, which is 3. So since the limit from the left is equal to the limit from the right, let's do f. Not going to write the x because it's too much work. Is equal to the limit as this goes to 1 of f of x. This tells us that the limit in totality of just x going to 1 is equal to 3. Very nice. So the limit does exist. That's pretty cool. Let's look at number 2. Hopefully that made sense. Number 2. The limit as t goes to -3. Man, I write very ugly. So we get, this is try plugging in it first. So we get 6 plus 4 times -3 over -3 squared plus 1. This is equal to 6 minus 12 over -3 squared. That's 9 plus 1. 6 minus 12 is -6. 9 plus 1 is 10. This simplifies down to -3 over 5. Pretty nice. So that was just a nice plug and chug. That's always going to be your first plan of action whenever you're trying to evaluate a limit. Just plug it in first. See what happens. All right, so let's plug in 0. H goes to 0. So when you do 6 plus 0, you get 6 squared, which is 36, and then minus 36 all over 0. So this is equal to 0 over 0. But this is not our answer, guys. You can't divide by 0. But not only that, we have a 0 at the top. This is what's known as a indeterminate form. That basically tells us, well, we can't really determine, well, what our limit was based off of this, you know? So since we got 0 over 0, this is a very common indeterminate form, that tells us that we have to do something to either know for a fact that this limit doesn't exist, or it does. So let's go ahead and try to do something. So I noticed that at the top we have a quadratic term. We should probably FOIL this out to see if anything cancels out. That's just some algebra 101 right there, guys. So let's rewrite this as the limit as h goes to 0 of, let's FOIL this out, so we should get 36 plus 6 times 2 times h, so 12h plus h squared minus 36 all over h. So if we do some canceling, so these 36's will cancel because 36 minus 36 is 0, and we'll be left with 12h plus h squared divided by h, and this is equal to the limit as h goes to 0 of, well, I can just factor out this h here on the top, so I'll just get h 12 plus h over h. These h's will cancel, leaving me with this nice limit, the limit as x goes to, or as, my bad, not x, where did x come from? Limit as h goes to 0 of 12 plus h. Well, now we can just simply plug in the 0, and we just get 12. So that tells us that that limit was actually equal to 12, and not 0 over 0. So yeah, just be careful with those indeterminate forms. That's probably the most common indeterminate form. 0 over 0. I can't really think of any other ones off my top of my head. Usually I think if you get like an infinity over infinity, I believe that's also indeterminate. Uh, these can be like plus or minus as well. Doesn't matter how you pair them. But yeah, infinity over infinity, 0 over 0. I think infinity to the 1 to the 0 and 0. I think that one, yeah. I think it's that one. Yeah. I don't know, guys. For sure these two. And so yeah, that was that's the end of this unit 1. I have no idea if I'm going to keep doing this. Probably. I'm really bored. Yep. Thank you guys. Have any questions in the comments? If I said anything, go ahead and flame me. I don't really care. I like math and I want to teach math. Thank you.